on the road. So we're going to be talking about piecewise functions today and tomorrow, but we're going to start with a kind of an Algebra 1, Algebra 2 level overview intro example, okay? So we are talking about Madison High School, who are selling flower bouquets. Madison High School is selling flower bouquets, and they are attempting to sell them so that they can raise money for their senior junior prom. Okay, that is the story. That is the story scenario for our example. Okay, now they first have to figure out, okay, how much money do they have to invest into this project? Okay, because you got to spend money to make money, guys. You got to spend money to make money. And it looks like they need to pay about $3 per bouquet to have them made. And there's an initial shipping fee of $15. Okay, so we have our cost per bouquet of $3 and our shipping fee of $15. So they start doing the math. If they only buy one bouquet, it's going to cost $18. If they buy 2 bouquets, it'll cost $21. If they buy 3 bouquets, it will cost $24. And we end up with a linear expression expressing the cost in dollars of the bouquets, okay, being 15 plus 3x. And if we look at this line right here, we can see that the cost that they are investing into this project increases by $3 every additional bouquet, with the initial $15 shipping cost being our initial investment. Okay, so question 1, this is a linear function. Question 2, we are going to write a function. Well, the function is right here, guys. The cost per bouquet is going to be 15 plus 3x, where x represents the bouquets. Pause here briefly. So the cost is the investment. This is how much they have to spend. This is how much money they have to spend in order to get the supplies to start selling said bouquets. Okay, this is the amount of money they have to invest into this project so that they can have the bouquets to sell. So we have our linear cost equation, linear function, and we have our cost equation of C of x equals 15 plus 3x. All right, I see most people that are participating have written this in correctly. Make sure that we have the C and we don't have double parentheses. But at this point, I'm gonna kind of move on. Okay. So the other part of this is, okay, they're buying all of these bouquets. What are they going to sell them for? So when we sell something, that represents our revenue. Our revenue refers to the amount of money that the student council will bring in as a result of sales. The revenue is separate from the cost. Note that. They apparently decide initially, this is going to change later, that they're going to sell the rose bouquets for $20 per bouquet. They are going to make money, guys. They are going to make some money. Apparently, in the first 5 bouquets that they sell, they could potentially bring in a revenue of $100. If they sell 10 bouquets, they could bring in $200. If they sell X bouquets, they are going to bring in a revenue of 20 times X. Okay, meaning that our function rule, aka question three, our function rule for sorry, pause for announcement in the background. Our function rule for our revenue is that the R of X equals 20X, 20 representing the price of the bouquet that they are going to sell it for. And pause here briefly to watch the answers roll in. Very briefly, my friends. So number 3, our parentheses x, close parentheses, equals 20x. So now in question four, we're going to kind of put all of these together because we have our cost. How much we're investing in this project. We have our revenue, how much we are going to make in sales, And now, my friends, it is time to concern ourselves with the profit. The profit refers to the amount of money remaining from all of the revenue once the cost has been covered. So profit equals revenue minus cost. Let's make note of that. Profit equals revenue minus cost. Profit equals revenue minus cost. Something to keep in mind if you ever decide to go into business of any kind. You always have to pay out your supplies out of any money that you make, and what's left over is your profit. Now, you want your profit to be in a positive, you want to make money, so your revenue needs to be greater than your cost. So, because the student council is good mathematically sound people, they decide to crunch a few numbers. Okay, they're like, okay, if we sell 5 bouquets, we're going to make a profit of 70. If we sell 10 bouquets, we're going to make a profit of 155. If we sell 15 bouquets, 20, 25, 30, so on and so on and so forth. So the more bouquets that they sell, the more profit that they are going to make. So far, so good. But now they want to be able to project further down the line. Okay, well, would it be worth the investment? Would it be worth the investment to order more than 30 bouquets? Because to a certain extent, depending on how their sales model is, they might have to pre-order all of these bouquets before they make their sales, especially if the student council is literally sitting outside of the prom selling these. Something to keep in mind. So they want to be able to predict what their profit is depending on their sales versus their cost. So we're going to write a profit equation. Now, the profit equation is going to be very similar to what we just said. The profit is equal to the revenue minus the cost. Now, we have previously defined the cost equation as 15 plus 3x, and we have previously defined the revenue equation as 20x. So putting this all together, we are now combining two functions. We are combining our revenue and our cost equation. Our combination is through subtraction. The operation of our combination is through subtraction, but we are still combining two functions. So we're going to have 20x. We're going to have 20x minus, and this is the very careful part, the whole cost equation. All right, so we're going to remember how parentheses work. And now I would like you guys to simplify this for question 4. So for question 4, you guys are going to have profit. Oops, that was an R. You're going to have profit of X equals, and I'm going to tell you guys it's going to be something minus something. This should be a 2-term equation once you have properly simplified this right here. If you cannot think about how to simplify this, that would be an acceptable answer for 4 for like a 3-point answer. Okay, so if you can't kind of think about how to simplify that, if you just guys want to write that pre-simplified answer down for the 3 or 2-point answer, that would be fair as well. I'm going to pause here briefly while I see the answers start to roll in on the formative. All right, I'm seeing several of you writing your equations. I'm not going to spend time grading any of them right now. Those of you who went for the 3-point answer, I will come back and make those adjustments later. For the sake of the recording, I am going to move on. There is nothing going to be to write down for a really long time, so don't worry about it. You guys can still kind of sit on question 4 for a little while, okay? And make sure that you're completing the simplification of p of x equals 20 minus 15 plus 3x with parentheses, okay? Now, here's the deal. When we start looking graphically at the data, we're looking at the profit being the difference between the cost and the revenue. So in this scenario, we're combining 2 functions using subtraction, which is all well and good. But now, because this is technically really kind of like an algebra level problem, now we've got to kick it up to some pre-calculus level stuff. So the student council supposes that after they've sold 50 bouquets, they might need to reduce the price to start to appeal to some of the other students who maybe couldn't quite afford the $20 initially, but maybe they're now running towards the end and they're just trying to get rid of the last of their supply. So they decide that after they have sold the first 50 bouquets, they're going to reduce the price per bouquet to $15 to try to sell off the remaining stock and keep the bouquets in demand. So we have a new part to our function. We have a new part to our function that is defined by a specific value of the domain, okay, by the specific value of the domain. And this is as such that our revenue function now has 2 parts. Our revenue function now has 2 parts. For values of X bouquets between 0 and 50, we are going to use the initial revenue equation of 20X. For any number of bouquets sold over 50, we will have a revenue equation of 15X. This is actually, in the grand scheme of things, going to affect our profit equation, because that's going to go from 20X minus 15 plus 3X to 15X minus 15 plus 3X. Now, while they don't do it in this particular example right now, this is something to consider moving forward, okay? And this actually might pop up in a later example or perhaps a later constructed response. Hint, 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 hint. I hope I can write, guys. All right. So this is where we introduce ourselves to the idea of a piecewise defined function. A piecewise defined function is literally a function that has pieces, okay? It's got 2 pieces to it. We could have a piecewise function with 3 pieces. You could have a piecewise function with 4 pieces or 5 pieces or however many pieces it wants to have, okay? But a piecewise function is literally a function that has pieces. And thus we start to get to the meat of the pre-calculus nature of this idea, okay? The pre-calculus nature of this idea. And thus ends our example about the bouquet of flowers. Now, we're going to end on one more example. This is kind of like the first example. Well, okay, actually, hold on. I'm jumping the gun just a little bit, because we do have the revenue equation graph. And I want you guys to be very clear, and I'm going to come back here real quick. This right here is just kind of left over from Agile Mind. So ignore the, let's see if I can hide it. Ignore the orange part of the line here that's just kind of left over from Agile Mind. So I'm going to kind of wipe that out for a second. So just to be clear, this is a graph of the 2 parts of our revenue equation. And as we're looking at our revenue equation, what I want you guys to notice is that we are being very strict about our domain in our graph. We have from 0 to 50 be part of our original revenue equation at a rate of $20 bouquet. You'll notice that we have an open circle at 0 because we note that 0 is not included, but we have a filled in circle at 50 for our blue $20 equation because 50 is included in the domain of the first part of this equation. We then have another dot at 50, but this has an open circle because we are representing the fact that at 50, the 50th bouquet is still going to cost $20, okay? But every bouquet after the 50th bouquet is now going to cost only $15, all right? And thus this will be the piecewise graph, This is the moment where I forget how to spell pieces. The piecewise graph of the revenue. And I want you guys to note, it's called a piecewise graph because it's in pieces. There's 2 of them. You can see the pieces. Okay. So the example that we are going to finish on, looks a lot more complicated than it is. We're talking about an astronaut above the surface of the Earth. And we make note that her weight is inversely proportional to the square of her distance from the center of the Earth. In other words, the farther away she is, the weaker the gravitational force between Earth and the astronaut. I could spend a lot of time explaining the physics behind this, but we're going to just kind of gloss it over and focus on that. Okay, so when she is above Earth's surface, we are dealing with an inverse proportional relationship. The further away from the Earth's surface, the less she will weigh. Okay, however, if she is on the Earth's surface, or even perhaps below the Earth's surface, the relationship is directly proportional. Okay, so given this, we have the fact that Earth's surface technically is a midpoint because the Earth has a surface. It also has a center. So we have segments. Actually, I'm going to go with white. That we have below and we have above with this kind of clear boundary line of the surface. Now, from the center to the surface is approximately 4,000 miles. Okay, it's approximately 4,000 miles from the center of the Earth to the surface, 4,000 miles approximately. So what we're going to do is we're going to use our newfound ability to have piecewise functions to create a full gradient function of this astronaut's weight. Okay, and we're going to use it in proper terms. So since a person's weight is inversely proportional to the square of the distance, we're going to have that her weight is equal to some constant divided by x squared, where x represents the distance from the center of the Earth to the person. Okay, knowing that the distance from the center of the Earth to the surface is 4,000 miles, this is going to be used for all values of x greater than 4,000. Then we have what's going on or below the Earth's surface. And this is where we have our directly proportional relationship. And this is going to be for x values between 0 and 4,000. We're going to put these together. We are going to put these together to have a piecewise function. Our piecewise function is divided into 2 pieces as such. The scan out. It's on the shelf. Our first piece is the proportional, directly proportional portion for values of x between 0 and 4,000. And then we have the inversely proportional part for values of x greater than 4,000. Now it is known, for the record, this is going to correspond to question 5. It is known that at the surface, the astronaut weighs 150 pounds. So, and that is at x equals 4,000. Now, for x equals 4,000, we are technically supposed to use the first equation. Okay, so b of x equals 150 when x equals 4,000. That should be 150. 150. So we can real quickly solve for B. B ends up being 0.0375. All right. Question is, what about A? Well, let's see. Okay. If we're at the surface, and if this is a continuous function, we should be able to use the same feature. Okay, like 1 inch, like in the grand scheme of unit scale here, 1 inch above the surface is still technically above the surface, but pretty close enough that you can probably still weigh 150 pounds. So we're going to do the same thing. To solve for A, we're going to set it up that A over x squared is going to equal 150 when x equals 4,000. And you use some algebra skills here, guys, and you solve for A. And A ends up being 2,400,000,000. It's a big number. So we now have our true piecewise weight function of 0.0375 x if x is for values of x between 0 and 4,000. Don't forget to scan back in. And 2,400,000,000 divided by x squared if x is greater than 4,000. And that, my friends, is question 5. And we once again, slightly more complicated piecewise function, but still a piecewise function. And don't worry, I'm going to come back to this. And we can see the first half of our data from counting in 1,000, 1,000, 2,000, 3,000, 4,000, as we go from the theoretical center of the planet to the surface of the Earth and what her weight would be doing. And then afterwards, going by 1,000 above the surface of the Earth, we're going out in space. And when you go out in space, you get that weightless feeling, so it starts to decrease again. And we can see the relationship between the initial linear portion and then the declining rational portion of our graph. And once again, we have a function that is in 2 pieces. We have a function that is in 2 pieces. And that, my friends, more or less is where we are going to end things for today. So yeah, hold please.